So in this video, we're going to talk about how to use linear programming to maximize or minimize a function. So remember, when we were solving systems of inequalities, we were finding solutions in the region where all of the shading overlapped. This region is also called the feasible region, and it contains all the values that are solutions to the system of inequalities. So for example, you can see here that 1, 2 is the only point that's within the feasible region. So all these other points are not going to be solutions to the system. So, when we looked at word problems related to systems of inequalities, remember we talked about some different situations. We were trying to figure out the value of two numbers, and then we talked about a bakery that was purchasing pecans and a person who was buying snacks for his friends. But in all these cases, we were trying to find the set of possible solutions, right? Because we were given a solution, we were said, well, does it make sense for that to be in this problem? Well, what if instead of that, they were asking us to find the least or greatest value within the solution set? So, what if the problem from the previous video had said this? So, remember, we had this Barbara's Bakery question where they were starting to bake pecan pies and they were needing to order pecans from two different distributors. So, remember, they had these following conditions, and then we took those conditions and represented them using these inequalities. So, what if instead of finding a possible solution, this problem had said, how many pecans should they order from North Texas and San Saba to minimize the total cost of ordering pecans? So that's a little bit different than just finding one solution. So to figure this out, we're going to use a process called linear programming. So to explain this, I'm going to have to go through some vocabulary and definitions before we actually get to the problem. So just bear with me for a minute. So what we're going to do is we're going to start off by writing a function that represents the total cost of pecans. So this representative function is called an objective function, and we usually call it f of xy. Okay, because we have two inputs. We have variables x and y that are going into this function, and then we're going to use that to determine whatever value it's asking us for in the problem. So then we're going to figure out what value of x and what value of y is going to maximize or minimize this function. And so this is a process called optimization. And you may have heard this word around a lot, right? So optimization is something that people are always talking about. They're always saying like, let's try to optimize this. Or, I just Googled optimize and this article came up from WikiHow that says 3 ways to optimize your PC. So we know what it means to optimize, right? So if this article is telling me how to optimize my PC, it's going to tell me how to make my PC perform better. Okay. So that's the idea of optimization. So to do this, we're going to use a problem-solving process called linear programming. And I know that some people see the word programming and get confused and think that we're going to start programming in computers, but that's not what we're doing. We're just using this problem-solving process to figure out the maximum or minimum value of our objective function. So what we need to do first is graph the system of equations that represents the conditions. Because if you think about it, when we were working on that pecan supply problem, they gave us a bunch of conditions, right? They said they have to process at least 35 pounds, and they said they have limited storage that can hold a maximum of 70 pounds. And then they had a limit on how much money they can spend, right? Because they said they can spend no more than $1,200. So all of these conditions are what we outlined in the system of inequalities. So we also need to figure out now the objective function. So in this case, we're trying to minimize the cost. So we need an objective function that describes that, right? The cost. So the total cost, we have this information from our word problem. It says pecans from North Texas cost 27.50 per pound, and pecans from San Saba cost 10.25 per pound. So we can use this information to write this objective function, f of xy equals 2750x plus 1025y. So now we need to figure out how we can optimize this function in order to minimize the total cost of pecans. Well, what I can do is I can take those conditions that I have outlined in that system of inequalities and I can go ahead and graph them in Desmos. So when I graph them in Desmos, as I've done here, you can see that we have this feasible region where all of the shading overlaps. Well, what's interesting about this feasible region is that it's a closed figure, right? And you remember back from geometry, the corner points of those closed figures are called vertices. So if I click on those vertices in Desmos, notice it'll give me the coordinates. So this feasible region has 5 vertices. And what we can do now is we can plug the vertices of the feasible region into the objective function. And then we can look for the least value because in this case, we're trying to minimize. Okay. And so these vertices are going to help us optimize our function. So for example, if I plug in the first vertex, okay, so I'm going to go to this objective function I have here. And if I plug in that 0, 70, so I have f of 0, 70. And so that's going to be 2750 times 0 plus 1025 times 70. So when I do that, I just went ahead and did that in my calculator. And so that gives me 717.5. Okay, so I'm going to repeat with all of these vertices. So I have f of 0, 35. So that's going to be 2750 times 0 plus 1025 times 35. And when I do that on my calculator, that gives me 358.75. Okay, and then I have f of 35, 0. And so that's going to give me 2750 times 35 plus 1025 times 0. So when I do that now in my calculator, that gives me 962.5. And then I have f of 43.6360. So that's going to be 2750 times 43.636 plus 1025 times 0. And that's going to equal, it's like 1199.99. So I'm going to round that to 1200. And then I have f of 27.971, 42.029. And so that's going to be 2750 times 27.971 plus 1025 times 42.029. And if you do that on your calculator, that's once again going to be about 1200. So if I look at all of these values that I got right here, the smallest value is actually this 358.75. Okay, so if I'm going to advise this bakery on how to minimize the cost of ordering pecans, I would say 0 pounds from North Texas, right? Because remember that was our X value. And I would say order 35 pounds from San Saba. Okay, so that's how you can use those conditions and this objective function to optimize a situation. So here's a summary of what we did. So we optimized a function using linear programming. Remember, we first identified the conditions of the problem. So we wrote a system of inequalities to represent these conditions, and then we graphed the system of inequalities. Then remember, we found the feasible region and we identified the coordinates of the vertices. Then we wrote the equation of the objective function that's going to be maximized or minimized, and we substitute the coordinates of these vertices into the objective function. And then we use that to determine which vertex gives us a maximum or minimum value. So remember, when we're going to work on writing those inequalities that represent those conditions, we may need this chart of, how to translate words into inequality signs. So make sure you have this available to you as we work through these problems. So let's try a new example. So it says that Lisa is the owner of a hair salon, and during a week, she plans to give X child haircuts and Y adult haircuts. She charges $10 for child haircuts and $40 for adult haircuts. She would like to make at least $1,000 during the week and provide no more than 40 haircuts total. How many child X and adult Y haircuts does she complete during the week to maximize her profit? Okay, so a lot going on in this problem. I start off with our variables. So we have X child and Y adult. Okay, so I saw some of those important inequality phrases in this problem. So she wants to make at least $1,000. Okay, so the amount of money she makes from a child haircut, well, let's see what that is. She gets $10 for a child haircut. So the total money she makes X haircuts would be 10X. Okay, plus how much money she makes from adult haircuts. Well, she gets $40 for adult haircuts, and then she provides Y adult haircuts. So that's going to be the total amount of money she makes. Well, she wants that value to be at least, which remember is greater than or equal to, and then it's $1,000. Okay, so we have our first inequality. Now let's think about the next inequality. Well, it says that she wants to provide no more than 40 haircuts total. Okay, so remember, no more than is another one of our inequality phrases. So the total number of haircuts is going to be X plus Y, right? Because she provides child and adult haircuts. And no more than is going to be less than or equal to. So that's going to be less than or equal to 40. Remember, we also have those two additional inequalities since we're talking about a real life situation because we can't give negative child haircuts and we can't give negative adult haircuts. Okay, so we're going to add those two requirements in. So now let's think about how to graph this. So I'm going to go to Desmos now and graph my system of inequalities. So I have 10x plus 40y is greater than or equal to 1,000. And then I have x plus y is less than or equal to 40. And then my two additional conditions, x is greater than or equal to 0 and y is greater than or equal to 0. Okay, so now let's try to find our feasible region, and you can see that's right here, right? If I uncover these, there's my purple region of overlap, and then if I add in these two inequalities, you can see that this triangle defines my feasible region. So let's click on those points to find those vertices, and now we need our objective function, right? So the objective function, well, we want to talk about her profit, okay? So her total profit, f of xy, is going to be the money she gets from a child haircut plus the money she makes from an adult haircut. Okay, so f of xy is going to be 10x plus 40y. So now let's use these vertices to optimize this objective function, right? We have f of xy equals 10x plus 40y, and let's plug in those points. So we have f of 0, 40. Okay, that's going to be 10 times 0 plus 40 times 40, and that is equal to 1,600. Then we have f of 0, 25, which is 10 times 0 plus 40 times 25. So that's going to give us 1,000. And then we have f of 2020, which gives us 10 times 20 plus 40 times 20. Okay, and that's also equal to 1,000. So you can see that 1,600 is the largest value. In this case, we're trying to maximize profit, so we're going to look for the biggest value. So 1,600 is the biggest value, so that means 0 for x and 40 for y. So that means that 0 child haircuts and 40 adult haircuts is what we're going to tell her is going to be used to maximize her profit. So now you can go ahead and pause the video and try doing this example on your own. So now let's talk about the solution to this problem. So Antonia designed stickers and art prints for her store. So I went ahead and defined stickers as X and art prints as Y. So she can create no more than 30 new designs per week. So the total number of designs X plus Y has to be less than or equal to 30. She also would like to earn at least $90 in a week. So 2 times X for the amount of money she makes selling stickers, and then art prints are $5, so 5y for the amount of money she earns from prints. So the total of that has to be greater than or equal to 90. Also, since we're talking about a real life situation, you can't make negative stickers or negative art prints. Both of these values, x and y, have to be greater than or equal to 0. So I went ahead and graphed all of these conditions in my coordinate grid, and then notice that we have this feasible region right here, right? So it's like this triangular shaped region. So let's click on the points to get the vertices. Also, we want to think about what we're trying to optimize in this problem. She wants to maximize her weekly earnings, so we need to write an objective function that represents her earnings. Well, she gets $2 for a sticker and $5 for a print, so the objective function will be 2x plus 5y. So what we can do now is plug in each of these vertices to figure out where we can find the greatest value of the objective function. So the greatest value of the objective function is here at 150, which is given to us by x equals 0 and y equals 30. So that means that to maximize her earnings, she should make 0 stickers and 30 art prints. So here's another problem. Let's try this one. So it says Sunrise Bakery makes specialty breakfast muffins in two sizes, large and small. It takes 4 ounces of chocolate chips to make a large muffin and 2 ounces of chocolate chips to make a small muffin. They can use no more than 32 ounces of chocolate chips in one day. The profit on a large muffin is $5 and the profit on a small is $2. They want to make sure not to disappoint their regular customers who order at least 2 large and 4 small muffins per day. How many large muffins X and small muffins Y should they make in a day to maximize their profit? Okay, so let's start off with our variables. We have X large and we have y small. So let's think about the conditions that they have to follow. Well, it says that they can use no more than 32 ounces of chocolate chips. Okay, so each large muffin is going to require 4 ounces. So we have 4 times the number of large muffins, plus every small muffin needs 2 ounces. So we have 2y, and no more than means less than or equal to, and then we have 32. Okay, so that's our condition about the chocolate chips. It tells us about profit, but notice in this problem, it's a little bit different than the previous ones. There's no conditions on the profit, right? It doesn't say they want to make at least this much money in one day or they want to make more than a certain amount. However, we do have some conditions on the number of muffins they want to make, right? So for their regular customers, they need to make at least two large muffins. So at least is going to tell us we have x greater than or equal to 2. And also they want to make at least four small muffins. Okay, so we have to have y greater than or equal to 4. So let's go ahead and go to Desmos now and graph these inequalities. So we have 4x plus 2y is less than or equal to 32. And then we have x is greater than or equal to 2 and y is greater than or equal to 4. Okay, so now you can see here we have this region of overlap. So let's click on those points to find those coordinates. And now let's figure out our objective function. Well, here we need to figure out how to maximize the profit, right? So our objective function needs to represent the profit of the bakery. Well, remember it says that they make $5 on every large muffin, so that's 5x, and they make $2 on every small muffin, so that's going to be 2y. So we're going to use the objective function to represent the profit. So now let's take this objective function, our f of xy equals 5x plus 2y, and let's plug in those vertices. So we have f of 212, so that's 5 times 2 plus 2 times 12. So that's going to be 10 plus 24, which is 34. Then we have f of 24, which is 5 times 2 plus 2 times 4, which is 10 plus 8, which is equal to 18. Then we have f of 6, 4, which is 5 times 6 plus 2 times 4. So that's going to be 30 plus 8, which is 38. So if we look at all of these values, notice that the maximum value occurs here, right? When x equals 6 and y equals 4. So we're going to tell the bakery that they need to be making 6 large muffins and 4 small muffins in order to maximize their profit. So now you can go ahead and pause the video and try doing this example on your own. Okay, so now let's talk about the solution to this problem. So they make two types of bicycles, the cruiser and the racer. So the cruiser is what they're calling X and the racer is Y. So notice that we have one of our conditions, they can spend a maximum of 360 hours a month assembling bikes. So if they spend 1 hour on a cruiser and 3 hours on a racer, that means 1x plus 3y has to be less than or equal to 360. Also, they have limited storage, so they can store no more than 300 bicycles in their warehouse. So that means that the number of cruisers plus the number of racers, which is x plus y, has to be less than or equal to 300. So we also have to add in those conditions since we're talking about a real life problem. We can't make negative bicycles. So we have to have x is greater than or equal to 0 and y is greater than or equal to 0. So I've graphed all of these inequalities here in Desmos and notice that we have here our region of overlap, our feasible region. And if we click on those vertices, we can find the coordinates. Now we need to write our objective function. Well, in this case, they're trying to maximize their earnings, right? So earnings is what our objective function needs to represent. So they make $300 on a cruiser, so that's 300x. And they make $600 on a racer, so that'll be 600y. So 300x plus 600y will be our objective function. So now we're going to go ahead and plug in all of those vertices into our objective function and notice that the maximum value we get is 99,000, which is the result when we have 270 cruisers and 30 racers. So that's what we're going to advise this company to do, right? So make the 270 cruisers and 30 racers in order to maximize their earnings. So we can use optimization with linear programming to figure out the maximum or minimum values of a situation. Once we graph a system of inequalities to define the conditions of the problem, the vertices of the feasible region will give us the values that will allow us to optimize the objective function.